streaming is on, recording is on. Light, so is it too much light? You want to do it down? Okay. Okay. We'll do that. Is it on? Okay, so lecture idea 12. So what will happen today is that there are actually three items that I would like to discuss today. First one is associated to flexible bodies. So I would like to close the case of flexible bodies, and that requires to explain you one more way that the flexible bodies can be described. That will take a little bit from the beginning of today's lecture, and then the main body of today's lecture is actually the real-time simulation, which we will get started after, say, 15 minutes or 20 minutes or so. And then what follows is recap, summary. And that summary covers the material that I'm expecting you to know when you're entering the next midterm exam, the second midterm exam. Okay, so without further ado, next midterm exam, the voting is closed. And here's the result. And the middle option got the most of the votes. So if you look at the percentage is 44% was voting that exam should be in a week 50, and that week is the one. How is my streaming? Voice. Okay. So let me take a look. I was quite, almost about, this close to say that look at my streaming today, because it should be like with no technical difficulties whatsoever. Let me see where the problem is coming from. So this is correct. Is this a mic here to? Okay, so is this helping at all? Is it possible that online participants can make me a comment if it gets still problem? Okay. Is this helping? So maybe it's well, I have a new computer today, but I don't know where the echo could come from. Is it helping at all? It's working now. Okay, that's good. So it was about that camera was using a mic as well, so it's actually muted now, so it should be all right. So let me go back to my presentation. I'm very proud of this because with my new computer, which by the way is not making any sounds whatsoever, the previous one was making that dying noises. That is missing. How come that is missing? So was it on there already? And now it is back on. Okay, so yeah, I was just telling about how proud I am with my new computer, which is not making any sound whatsoever. And not just that, but I finally figured out how to make nice streaming art. Look at how it is. So for you it looked perfect, and for online participants too, it should look perfect too. And it took me 11 weeks to figure this out, which is, not that bad because finally the last lecture will be with that should be perfect. Okay. Anyway, so I was about to explain that the option related to week 50 was the winner this time. So the exam will be put on Monday, December 9th at right after the midnight, and it will be closing on Sunday, December 15th. Okay, that is not needed at just before the midnight. So those is that is a time period that you can make your 2 attempts to do your midterm exam, second midterm exam. And again, keep in mind that if you wanted to pass the written exam part of the course, then by using this midterm exam option, then you must participate to both midterm exams. Otherwise, you need to go and participate the written exam, which, if I remember correctly, will take place on December 16th. Correct. Or you don't remember that. You don't need to remember that if you are planning to take midterm exams. Okay, so just shortly, let's summarize what we discussed last week. And last week we completed the discussion about the hydraulic modeling, and we look at the two components. The first component we looked at was the hydraulic cylinder, which is a very simple hydraulic component, and that's the one that is converting the hydraulic pressure to be the mechanical force. And it goes such that, the pressure that is applying here in the piston side will be multiplied by a corresponding cross-section area, and that is then subtracted from the pressure that is applying in the piston rod side, and that is then multiplied by, again, corresponding cross-section area. That's the net force that the hydraulic cylinder is capable to produce. Then, due to the sealings that is here, to prevent oil coming off from the cylinder and to prevent oil to travel through the piston, there is a friction force. And the friction force is typically something where the stick-slip phenomena takes place. By the way, often asked question in a written exam, what is a stick-slip phenomenon? And that's the fact that that static friction is higher than the sliding friction. And that's the one that is causing that noisy movement, which can take place also in a hydraulic cylinder. Then also last week, we shortly looked at the pump models. And generally speaking, we have two different types of pumps. So we can have fixed volume pump. And in the case of fixed volume pump, we need to compute two equations. The one that is limiting the flow rate based on the power, and another one that is limiting the flow rate because of the geometry. And then selecting the one that is producing the lowest numerical value. This is a pipe pump. The fixed volume pump type is still out there and is often used if there is a application that is very critical in terms of reliability. Anyway, so the project or the problem associated to fixed volume pump is that it is keep on producing the energy to the system whether or not it is needed. And to make that more clever, we can use a variable flow pump. And in a variable flow pump, the flow rate can be computed by using a differential equation. And this differential equation is a first order differential equation where this is reference pressure, this is a pressure measurements right after the pump, and this is a flow rate that the pump is producing at any given time, and this is a time constant. K here is a semi-empirical parameter that can be obtained from manufacturer's catalog. So that was a last remaining components in hydraulics, and then we step into the flexible bodies. And now, in flexible bodies, how is a picture at the moment? The picture at the moment is such that commercial software is that are focused on multi-body system dynamics. They can, of course, handle the cases and systems where all the bodies are assumed to be rigid, and they can also handle the cases when there is a small deformation. And the small deformation that can be captured or modeled by using the method that I'm about to explain to you next. Then, which is, some of the commercial software is able to do it today. Some are still looking the ways to do it. Is related to large deformation. The difference between the small, this one, and slot deformation is how is that strain displacement relationship is accounted. If we are assuming displacement strain relationship to be linear, that means that we cannot capture large deformation. In turn, if this relation is nonlinear, then we can capture the large deformation. And then it's also possible that there is a material nonlinearity, which tells that then the strain-stress relationship, this is a stress, this is strain, is nonlinear, which is not often the case in machines. Okay, so with that, then the one more slide about the summary. We look also at the lump mass approach, which is not strictly speaking within the family of flexible bodies. And is not in a family of flexible bodies because this is an extension of rigid bodies. How it goes? It goes such the way that originally, typically a beam-like body is divided to a number of rigid bodies. And what comes between these rigid bodies is the spring elements that is introducing the coefficients or spring coefficients to all 6 degrees of freedom. So this approach is not requiring any extension in a theory because it is still using rigid bodies. Springs are external applied forces, so actually no need to change anything what comes in a theory. Problem associated with this method is that it easily leads to a numerically very inefficient models. And inefficiency comes from the fact that there are very low frequencies and very high frequencies associated with this structure. Low frequency, if you think about the beam-like structure, could be deformations associated to like bending. So when you look at how is a frequency associated to bending deformation, that's typically very low. If you want to know the numbers, say 50 hertz or less is a typical value that you can find. Same time, this structure includes the axial vibration. If you think about that, this body and this body can move relatively with respect to each other in axial direction, meaning that there is a somewhat short beam which is actually deforming in axial deformation, meaning that frequency associated to that kind of deformation is very high. How it look? Well, in response-wise, it looks such that if this is let's just say that this is a time and then this is a random response associated to this particular structure, it looked like, if there is like a loading of this structure, it looked like this, so no surprises. But when you take a close look, when you magnify the details of this curve, let's say that this particular point, when you look how is the response includes high frequency vibration. And this high frequency vibration is something that indicators are able to detect. They realize that something is moving there, although that in a big picture it makes no difference whatsoever. But the integrator is able to detect this one here, and then they will adjust their time step such that this high frequency vibration is captured as well. And that's the one that slows down the computation. And that's why the good modeling policy goes such that you wanted to set all the frequencies to be close to each other. It doesn't really matter if they're high or low, but they should be somewhat close to each other. And that guarantees or it helps to compute things efficiently. Okay, now the final thing, let's close this case about flexible bodies. So finally, the final thing that I would like to explain here is actually the policy that is used very much in today's industry. And this policy to model flexible bodies is called the floating frame of reference formula. It's a monster name. But what I would like you to remember out from this monster name is that this is a method that actually combines finite element method and multi-body system dynamics. So it goes such the way that you are actually starting from the kinematics, and you're looking how the kinematics of a deformable body can be described. And example is shown here. So Here I have now potato-shaped body. This is in three-dimensional space, so it's a spatial case. And I have here one point, which is called P again. So it's a particle P that we are very much familiar with. And now if you look at how we describe that in the case of rigid bodies, we describe that such that we first describe the translation of body reference coordinate system with help of vector R. We're going to do the same here. And then we're going to describe the orientation of body reference coordinate system with rotation matrix. So everything is what we are used to deal with. And then we are saying that on undeformed configuration, the particle P is located in a point that vector U bar 0 is defined. And then comes one additional component to our kinematics. And this additional component is a vector U bar F. That's the one that tells how is the deformation of this deformable body. Now, this vector U bar F, this is the one that we will describe by using a finite element method. And that's how we can combine large relative translation, which is the vector R, large relative rotation, which is a rotation matrix, and deformation, which is actually coming due to this component. That's in a nutshell the method. Then there is some other details, and kind of like for your information this time already, is that the floating frame, this body reference frame that is described here in this particular method is called floating frame, because under certain condition it can actually be detached from the body. But we don't need to care about that today. Later, this is a subject matter that we can discuss later. Let's just call that's a body reference coordinate system, and that's the one that describes the large rigid body translation and rotation, and then the small deformation with respect to body coordinate system. That's the one that is described by a finite element method. If you haven't heard about the finite element method, that's fine, because I'm not going to go deeper than that in my today's lecture. Okay? All right, so here's again the big picture. Let's just say that I'm not going to go deeper than that in my finite element explanation. Obviously, I go a little bit deeper than that because there's one more slide that tells how exactly it is that the vector U bar can be described. Well, just shortly, here's equation of motion that comes from a finite element method. And that equation of motion describes deformation of this potato-shaped body. And we can use almost any kind of elements we want, but we can typically use solid elements, plates, and beams to describe or discretize this body that we are assuming to be deformable body. Once we do that, mathematically, equation of motion look like this. So I have here again inertia forces, elastic forces, and externally applied forces. And what I'm doing then is that I'm solving this vector U bar, and I'm substituting that vector U bar to my kinematics, and that's how I can account the deformation. It's a bit lengthy story, but this is in a nutshell how it goes. You happy? Okay. There is one problem associated to this. The problem is the fact that when you look at the usual size of your finite element model, this one, that typically consists of, say, 10,000 degrees of freedom, 100,000 degrees of freedom, million degrees of freedom in some cases. And now things are not matching that well any longer, because for a single body, you need here 6 or 7 generalized coordinates in spatial case to describe large translation and large rotation. So then if you're using 6 generalized coordinates to describe the large translation and rotation, and then million coordinates to describe the deformation, it's making no sense, because the one is rough and one is very, very detailed. So we have to do something to this finite element model. And the technique we are doing for that is the one that Professor Sopan is already explaining to you, those of you that are participating to use this class. So it's a model reduction technique that we are doing. So we are not using the nodal decrease of freedom that is explained here, but we are moving to another space that is called modal decrease of freedom. Can you hear the difference because of my accent? Nodal decrease of freedom to modal decrease of freedom. Nodal to modal. Seriously, this is a serious question because an accent makes it hear like degrees of freedom. But you hear the difference? Okay. All right. So what we are doing for this finite element method is that we are moving from this nodal space, from nodal degrees of freedom to modal degrees of freedom. Shortly speaking, what is that? That is assumed deformations that are multiplied by unknown amplification factor. And mathematically that can be explained as it is shown here. This is making it possible to reduce size of your original finite element method very significantly. You can go down to from 1 million degrees of freedom to say 20 degrees of freedom. You will lose something. Of course, you will lose an accuracy, but big picture in terms of dynamics, the compromises you are introducing may not be that significant, and it's typically acceptable level. How that goes in details, that I will explain you starting from January. That course that is I don't know if I remember, but there's this really good course that is called Simulation Laboratory course. Did I mention that already? I think that I haven't mentioned. So that's an awesome course. So consider to sign in. All right. So that's how it goes. So it's all about the deformation modes, and here is a few examples. So this is a biomechanical application where the bone structure. So the tibia. So maybe I should. So let's just run this, and after the animation is done, let me explain this again. So here I have tibia and a femur modeled as a flexible bodies. And the way how they are described, it is based on these modal degrees of freedom. And how they look like is like deformation modes associated with the bone structure. That you can describe by taking a volunteer, doctoral student. That's equal than the volunteer. And then, then you're doing computer tomography scanning and maybe the MRI scanning. Actually, you need the MRI scanning and CT scanning both. Then you can get the geometry of the bone, which is that case based on specific bone. And then you can compute, that you can create the finite element model that is describing your bone. And once you have your finite element model, then you can conduct eigenvalue analysis. And with help of the eigenvalue analysis, you are able to move from that nodal space to modal space. And now, if you're completely off what I'm explaining, if you are like, oh my God, nodal, modal, eigenvalue, none of this stuff makes any sense, that's fine. Because level of knowledge that I'm expecting you to have is this. Two methods are combined. And the two methods, that one is finite element method, another one is a multi-body system dynamics. That's enough. Okay, so let's look at how are these animations. So that's just the vibration mode of. I'm back. Yeah. So when